Oh, one sec. Yeah. Okay. Sorry. Okay. Yeah, I guess we'll get started. Hey, everybody. Welcome to our Intro to Machine Learning, Intro to Tech. Before I get started with my presentation in a bit, I guess I just want to give a couple of quick announcements about ACM here really quick. Oh, my bad. Okay. So first and foremost, our social plugs. If you'd like to just stay in touch with us and know what's going on in the realm of ACM, here are a couple of our social media links. We typically post our stuff on Discord pretty often, or more often than not. Every week, I think we get updates on the current week's events. So I would suggest you join that just so you know what events are coming up. But we do still have our calendar on our website, so you can always look at that, though I would suggest just being under Discord just so you know what's going on and it's more up to date. Moving on, just a brief recap about memberships. So long as you attend 9 meetings in the spring, or is it or fall, right? Yeah, 9 meetings in the spring or fall, you will get a free t-shirt at the end of the year. And you're also going to be invited to our banquet, and that's mostly for networking, just talk to other people or, others in the industry, and, just kind of hang out. And you're also eligible for any giveaways we do, which we have some occasionally. But those are pretty much some of the nice benefits we have here. And if you'd like to just sign in for today's meeting, feel free to scan that QR code. And for those of you who don't have phones and would prefer a link, I can pull that up towards the end. And yeah, if you didn't catch this now, we'll show it up at the end of this presentation. So, okay, moving on. I guess just upcoming events. So we are going to have our officer elections this Wednesday. So if you're interested in getting involved in ACM, and maybe you're curious about a position, so maybe the projects officer, right? Or that's what I do, or perhaps president or vice president or any of the other, or leading any of the other sub-organizations, we encourage you to run and join. Only thing is I will say that if you are running for a position, there is a Google Forms due tomorrow. I don't know what time, probably midnight. Yeah. And you can find that at, I didn't put it on the slide, but you can find that at elections.acmutsa.org. And you can see who's running, and you can also sign up if you'd like to. And also one last thing, ICPC. So if you're into competitive programming, learning about data structures, know how to solve problems, or take a more algorithmic approach to problems, ICPC is great for improving your skills. And I've been a couple times, and I have had great success. And it's good for you. So I would suggest you at least join one and see what's going on there. But these are held typically every Sunday, 11 to 2, I think. And they're hybrid, so you can either go in person or online on Discord. You'll find quite a bit of people there. And yeah, I guess once more, here's the sign in case you need it. And there's also a link there. But yeah, I'll give you guys a second there just to sign in if you need it. All good? I guess I'll move on. And again, don't worry, if you didn't get it, I'll pull it up at the end as well. Okay, without further ado, let's get started. So firstly, what is machine learning? Well, machine learning is the ability for computer programs to adapt and extrapolate from results, or create new results given some sort of data. So in typical programming paradigms or approaches, you're used to giving it some sort of input, then some sort of algorithm, and then you get some sort of output. So, for example, let's say you wanted to sort an array, right? So you'd expect the input to be some array, then your algorithm would sort that array, so from lowest to highest. It's like if you have a list of numbers 1, 2, 3, 4, 5, you'd expect it to keep like that because the algorithm just sorts it as such. Or more simply, maybe you have a function that adds 5, your input is 1, and then your output is 1 plus 5 because your function just adds 5. But in machine learning, however, this approach is different. So rather than giving the inputs, you are giving some sort of sample data or training data. That's what we typically call data that we are going to act upon in our machine learning model. And the model itself, that is actually what is this black box so far, that does all the work for you and, figures out what your data has, what's in common with your data, what kind of features or what kind of characteristics your data has. And then from said data, it creates a prediction. And, this prediction is basically the computer's idea of what this thing you're showing it is. What does the data you're showing it, what does it think that is? So for example, I have a couple pictures of frogs here. So, I guess the question is, why machine learning? I've given you a very basic premise that it's a little different than your typical programming paradigm or paradigms. But the question is, why? Well, for starters, I think it's pretty obvious that machine learning programs are much, much more flexible. So rather than having to rewrite your entire program for some sort of edge case, right? With machine learning, your results or your model may have already adapted to said results. Or, if there are some very strange outliers, it's not very difficult to change the program slightly and have your machine learning model adapt to said results. So let's take, for example, a frog here, right? Let's say we wanted to identify a frog, right? So a lot like how humans would identify a frog, we'd probably come up with a couple characteristics. They're roundish, they're mostly green, they have bulging eyes, so on and so forth. So in our traditional programming paradigm, we'd say, oh, hey, look, a frog is circular. It takes, some pixels of the screen, those are going to be green. And maybe we have some other white pixels for the eyes. But the problem is what if we just give it a green ball? What if we just have a white background and a green ball? The problem is that because we have hard-coded our algorithm to say, okay, well, if it looks green enough, if these pixels are green enough, then it must be a frog. So our algorithm gives us a false positive. So even though it's not a frog, our program thinks it's a frog. So the alternative approach here is, of course, machine learning. So we can give the computer an idea of how a frog should look like. Maybe we give it more features than just it's green, it's round, it has bulging eyes. There's more features we can talk about, and the computer or the model can act on it. So a lot like how, for example, a toddler would say, what's a computer, right? Like, this is a computer. It has a screen, or that's a computer, or that's kind of a computer, right? These, you can learn, like us humans, we kind of adapt from those results and say, hey, it has a screen, it has technology inside of it. Then it must be a computer. So in a similar way, that is how machine learning works. And that's sort of the big picture here. So, the question is how do we typically approach these machine learning problems? Well, so there's a couple of models or there's a couple of formats or ways in which we can teach our program to do machine learning. And so these are a couple of the ways we do it. So supervised, unsupervised, reinforcement, and instance-based learning. And so obviously there's many, many more aside from these, but just, for the sake of simplicity, we're going to, talk about these four very briefly. So supervised learning is basically when you have your data and that is fed into the model, right? And you explicitly tell it the examples or what kind of solutions it has. So maybe, going back to our frog example, let's say, we feed it in a couple of images of frogs, right? So, we would explicitly tell it, okay, this is a frog, and this is a frog. This is also a frog, but this isn't a frog, right? So we feed it these solutions. And these solutions are typically called labels because we label this data as what it is or what what it should be. And so like I said, there's alternative approaches. So then you have unsupervised learning. So the difference between unsupervised learning and supervised learning is that unsupervised does not contain labels. So, you may just throw the model a couple of images, you kind of give it solutions, and then from those, or I guess, well, you throw it a couple of pictures, you have your machine learning model, And then from all that data, you would run it through, and then it would say, oh, this is a cat, this is a dog, this is not a dog, this is not a cat, so on and so forth. And then there's the last two. So reinforcement learning is basically just rewarding your model whenever it achieves a target or good outcome. So for example, consider a robot or a bot that plays chess, right? So a good outcome would be that the bot wins chess versus the bad outcome is that it loses chess, right? Obviously you want it so that the bot wins more often than it does, or rather wins more often than it loses. So that's the key of reinforcement learning. So I guess quick question, how many of you know about AlphaGo? Okay, a couple. So this is a lot like AlphaGo, right? So if it wins a game of Go, you reward it for its positive outcome or the target outcome, and if it loses, obviously you don't reward it for said, you punish it, quote unquote, for its bad outcome. And finally, instance-based learning. So kind of as the name implies, it learns from instances. It learns from previous examples and tries to compare how similar your new cases are to your previous cases. So like, let's say you have, a couple of shapes. You've given it circles, maybe squares, and that's about it. But then let's say you give it an X, right? So an X, so it might think that the X is closer to a square because of how the shape looks like. Although perhaps it's not obvious. It might think that the X is closer to a square rather than a circle. And so, again, labels are considered the solutions to your data. And here I have just kind of a brief example of unsupervised learning. So, we give it the input data, the model does most of the work for us, and then it groups all of these images based on what they are. So are they cats? Are they dogs? Are they birds? So, maybe this is like a model that classifies animals. So, when we get our output, we get groupings of what kind of animal it is. But what do we actually call the task we do or we were performing with machine learning? So this is typically called classification, right? And so here's an example, right? So let's say you have a ton of emails, right? But then you want to classify what kind of emails those are. So it's like what type they are. So like you might have spam emails, or you might have important emails, right? So a little star on the top of your inbox, you might consider that an important email, right? So classification is a way of classing certain parts of your data, if that makes sense. And I guess before I move on, does anybody have any questions so far? All good? Okay. So now I'd like to talk about the most important part, data, and most importantly, data. Data is probably the most important thing. And perhaps I'm being a little pretentious about this, but I want to make it a point that it is super important to have good data. And there's a lot of pitfalls we have to be aware of. So is our data good enough? Is it of high quality? Is it of the kind of quality we want our predictions to represent, right? What about enough data, right? Do we have enough data to create our model? Or what about if there are red flags in our data? And so what I mean is like statistical anomalies, right? So outliers, errors, noise. But then there's also the issue of underfitting or overfitting our data. And what this means is like if we generalize a solution too much, right? Like let's say, for example, you get a bunch of random phone calls, right? So if you overgeneralize it, you might say that, oh, these random phone calls that I don't know of, they must all be spams or scams because 1 or 3 or 5 calls were. That might be overgeneralizing too much. And so for the more, I guess, statistically inclined viewers, you might have realized my talk about data means that statistics and mathematics are the heart of machine learning. It is a very, very important part of machine learning. And it does require a good background. However, I wouldn't be terribly intimidated because even with a little mathematics, you can still do a couple of things with machine learning. And, you can certainly learn these as you go. So yes, it is a lot of data. Yes, it is a lot of math. Yes, it is a lot of statistics. But I don't think there is a reason to worry because you will naturally get better at it if you do it more, that is, if you practice. So a lot like how I discussed, it's a lot about math, a lot about statistics. But the question is right now I've been saying like model. I've been saying the word model a lot, right? So I've been kind of thinking of it as it's an abstract thing. I've just been saying model, right? But the question is, what do these models actually do? How do these models actually act, right? So this is actually where all the math, the stats, and the algorithms do that for us. So we create some sort of mathematical algorithms, or I guess algorithms and mathematical models, and we represent, approaches to actually modeling this data. And so, a couple of examples include linear regression and gradient descent, decision trees, and logistical regression. So I wouldn't worry about the definition for all of them. We're only going to go over the first two. And statistics people are likely more familiar with regression, but even if you are not completely familiar, I'll still try to clarify as much as I can. And in my example here, I have a very simple decision tree. So like a decision tree is like branching down based on a yes or no option, right? So like in this case, like let's say we're, buying a house, right? Or estimating price or the price of a house, right? We might ask, how many bedrooms does it have, right? Does it have 2, 3, 4? What if it does? What if it doesn't? If it doesn't have 2 bedrooms, then it must be cheaper than one that does have 2 bedrooms. And I guess by not having 2 bedrooms, I assume that we have just 1 bedroom, right? So obviously, the more bedrooms you have, the more expensive it'll be. But this is just kind of intuition, sort of. So another question here, right? So what do we actually input for our data, right? Like I've kind of described, a little bit about this, right? Like I might say, oh, we feed images of frogs for our frog example. We just give it images of frogs. But, I think the answer is that there is a bit more than just feeding images, right? We also have to give it some sort of indicator, and these are called features. And features describe the characteristics or the independent variables of our data. So for example, for our frogs, right, we might consider what kind of color are they? How big are their eyes? Are they poisonous or not? How big is the frog itself? And so on and so forth. So, these are our independent variables. So I guess moving on, now I want to talk about what are the more foundational or basic models of machine learning, which is linear regression. And so I guess before I get into this, has anybody here, or how many people here have taken an introductory statistics course? Okay, so a couple of people have. So in your statistics course, you may have remembered that you have, when you have 2 variables, x and y, so your dependent and independent variables, you might say y equals ax plus b. So you might model, the relationship between your x and your y linearly. So a lot like in grade school or middle school, you would use the slope formula, y equals mx plus b, or excuse me, y equals mx plus b, and you would use that to kind of format a sort of linear relationship between your y's and your x's. So like maybe if I have y equals 2x plus 1, right? If my x is 1, then we expect our y to be 3, and if I have like x equals 2, I expect my y to be 5, right? So in statistics, we have sort of a similar concept where we model these 2 variables, our x and our y, linearly. And this is very, very simple. However, in machine learning, it's a little different. We typically use the theta notation. And so here I have theta 1, x1. I guess I mistyped that. My bad. Theta 1, x1, theta 2, x2, and then theta n, xn. And what theta means is it's typically representing a model parameter or feature parameter, so much like I described, it's part of the attributes we're interested in. But I think for now, the easiest way to think about this is just go back to grade school, right? Just think of it as a linear relationship between 2 variables. And I think to get across sort of what linear regression is about, and I'll come back to that picture in a bit, I have an example here with some data. So let's say, for example, we're interested in the relationship between the year a house was made and the price, right? So right now I have about 100 roughly. Yeah, about 100, rows of data between some year and some price to it. And so I think in the chat, I have linked a Google Collab, or it has been linked. And this is what we're going to use for the duration of our session. And I'm going to sort of try to go through this line by line just to give you an idea of what's going on here. So firstly, what we do here typically is we implement or we import our libraries. So in Python, this is typically done through the import, notation. And so matplotlib is just a plotting library, and I just implement that as plot. NumPy is a scientific or numbers related library. It's very good at processing numbers. And then pandas is good for statistics. It parses and reads CSVs quite conveniently. So rather than you having to fumble around, it sort of does more of the heavy lifting for you. And this sklearn, this is actually the machine learning library we're using. And so I'm just going to import the linear model. And this makes sense because our linear, regression, or like I said, is a linear relationship. And so from there, we're going to import that linear model. So first thing we do is we read the CSV. And then we can do that by doing pandas. We can do that by doing PD because that's pandas, and then read CSV, and then our file name. And let me actually clarify that really quick. So if you would like to upload a file, for example, on Drive here, which I think, yes, or yeah. So if you'd like to upload a file on Drive, what you can do is, do I have the data? Okay, I don't. What you can do is you can click this little upload button, and you can upload the CSV you need. So in fact, give me 1 second. I'm actually going to upload this. I'm actually going to upload it really quickly right now. Let's see here, 1 second. 1 second. Apologies. Give me 1 second. And while we're doing that, I guess I can get things. So really quickly, I'll just implement that. And then okay, I think that should do it. Let me just share my screen again. Sorry about that. Let's see. Okay, so I believe I'm sharing it. So what I've done is I've just uploaded our housedata.csv here. You can just do that by getting your downloads, and you can just drag it here, and that's fine. So right now, to our Collab, I've just uploaded this CSV that I've talked about. And so like I said, I'm going to read it. And then this describe method, that actually just gives us, so what this does is kind of tells us what the CSV is about, and it actually gives us some very nice statistics. It tells us like how many columns we have, right? The mean of our data, if it's numerical. If it's not, usually you get not a number or noun. It tells us the standard deviation, the minimum, and some other useful statistics we might want to know about our data. And so if I run this, hold on. Anyway, I think I probably here. Hold on 1 second. I had here. I guess here. Let me quickly see what's going on here. There you go. Yeah, you're right. Let me correct that. Okay, so just correcting my error. So it's in that sample data folder. Thank you. And yeah, so right now we just pulled up some really basic statistics about our data. And so now what we can actually do down here is we can actually assign our X and our Y, each column of our data. So we can do this by saying X is equal to HD dot year. And HD is what we've used as our panda data frame. And don't worry too much about pandas. Just for now, kind of worry about the machine learning part. But what you can do is you can do this. So you can do HD. So what you declared before, and you can use the dot notation to refer to whatever column or variable you'd like. Now, I believe if you do year, this is also the same thing, which let me see. Yeah, this is also the same thing. Whichever notation you prefer is purely preference, but both should work. I guess the only concern is that if your column names contain spaces, the dot notation won't actually work. So if they have spaces, you might need to just use this format instead. But moving on, what I've done here in this line is I have reshaped it as a two-dimensional array. So the thing with our linear regression model is that our dependent variable x, so that actually has to be a two-dimensional array. It cannot be one-dimensional. And so by default, this just makes it one-dimensional. And so I'm using this reshape function to make it a two-dimensional array. So that's what, and that's why I'm doing that, because we actually need that in order for scikit to actually analyze our data. And so then I do y equals our price. So take that from the price column. And so what I do here is I call this, so I call plt.scatter. So what that does is that this makes a scatter plot based on the points we have from our data here. So our x's and our y's. And finally, I show this data. So this here is more of a visual representation of what our data sort of looks like. So now the question is yes, I've shown you this data. How do we actually associate the relationship between this? So this is where something called correlation comes in. So correlation is essentially a value between -1 and +1, and that represents how closely correlated our x and our y's are in linear regression. Or I guess in more general terms, right? So if we use the model notation, that correlation might be for any number of variables. So we can see how, like, maybe x, let's say we have 3 variables, x, y, and z. We could see how x is correlated to y and z. Maybe we could see how y is correlated to x and z, and so on and so forth. And so we can actually access the correlation by doing here. We can actually do this by taking our data, and we can say core, and I believe that does it. And so if we print this using a print statement, we can actually see that there's a correlation between our year and our price, right? And so going back to our presentation really quickly. So basically, the closer the correlation value is to 1, the more linear of a relationship that represents. So even though, yes, these lines, so some of the ones with 1s, the lines are kind of skewed a bit, you do see a correlation of 1 because they're so closely correlated that it creates this linear relationship. However, what you do need to keep in mind is that there's a difference between having a straight 1 and a -1. So a -1 means that they are negatively correlated. So as our x gets further, right, or as our x increases, our y decreases. So this means they share kind of an inverse relationship. And then vice versa with a +1. So as your x increases, your y increases. And so you will notice, if our data is less correlated, then you will notice that there is more of a spread between each of our points. And so they don't look as linearly strong together as they would. So going back to our example here, we can see that, yes, we do see a line here. We do see sort of a positive relationship between these, but it's not as strong as if we were to have a purely linear relationship. So now let's take a look. Now let's consider actually analyzing this data. So what I've done here is first I have made our house model, and I have instantiated it with this linear regression here. So what this does is basically just uses scikit to take the linear model and then instantiates basically a class of linear regression. And then what I do is I basically fit this linear regression with my points, right? So the points I gave you in that CSV, I now use those points to fit, that within our data. And so now to actually test if our data does or doesn't work, or gives us somewhat of an estimator, what I've done here is I've picked 30 random points. So to see if there's a correlation between how old a house is and how more expensive it is, what I've done here is I've picked a random amount, or a random 30 random houses between 1970 and 2020, right? And then of those 30, what I have done is that for each of them, I want this model to predict, right? So to give me some sort of a prediction, or what it thinks the price would be given that year. And so once I've predicted it, I can once again show, well, just to compare our results to our previous values, our previous scatter plot, which is what we call the plot where we actually have our points scattered there. So what we do is we call our scatter plot, but then we also plot our new values, and we use this notation to actually make it a red line. And then we finally show our plot. And here I've also printed out the correlation. But anyway, this is our result. So you will notice you have all of our points kind of scattered around, but you also have the red line we drew. So you can obviously see that there is a positive correlation. So as the houses get, newer, the price is increasing. And I guess, so this is just one example of linear regression. But I guess for the more astute viewers, right, you will notice that even though I did give you some sort of data, right, this seems really arbitrary, right? Like, why is a house from 2005 more expensive than 2015? I mean, in some cases, yeah, sure, but let's say that they're all somewhat equal, right? Why is a house from 2000 more expensive than 2005, right? So you might notice that this data isn't quite right. It does look, it doesn't look random. It doesn't look like it's statistically correct. So that is definitely a pitfall in my data. However, I just wanted to show you, for the sake of example, how linear regression works, even though I agree that this data is likely not very good, simply because of multiple factors and how it was just sort of an arbitrary random example. But nonetheless, it's still worth considering in just showing an example of linear regression. So now I want to talk a little bit about our second model, gradient descent. So essentially what gradient descent is it uses an optimizing algorithm to find the local minimum of a differential function. Now, that sounds like a mouthful, doesn't it? And so the question is what does that all mean? So basically what it does is it tries to find, so firstly, we have something called the cost function, right? And so gradient descent tries to find the smallest cost function, or the minimum cost function. And a cost function is basically a prediction, or it's basically quantifies an inaccuracy between the actual values and a predicted value. And that's essentially what a cost value or a cost function is. And so gradient descent actually uses this, and we try to find like the values that create this minimum amount of inaccuracy or minimum amount of error. And so there are many gradient descent algorithms. So we have batch, stochastic, and I think another one I'm not actually sure of, but there's examples like batch and stochastic. But for the sake of my second example, I'm just going to briefly talk about stochastic gradient descent. And essentially what that is that in your data, it picks some random data, and based on only that sole point, it keeps taking the gradient. And for those of you who haven't taken calculus, the gradient basically is the partial derivative, or derivative of a vector in a direction. So anyway, basically, it tries to find the smallest change. It keeps trying to find the smallest change based on that one singular point you have picked. And so the thing with this is that it's somewhat good because it does give you kind of random values to work with, and it is fast, and it is good for large amounts of data, which you will see when I'm using the second example here. But it's not optimal, right? Like, there are probably better ways than just arbitrarily picking points. And so like I'm saying here, so we're going to actually have a classification example where we classify numbers based on some images. And for the sake of that, we're going to try to fit our data or predict our data using a stochastic gradient descent. I know that was a lot. Does anybody have any questions? Are we all good? Okay. So moving on. So once again, just importing my libraries and then import this. And so what this actually does is we can actually use something called fetch OpenML, and from a database, we can actually fetch, some sort of some data. And so what MNIST so we're using that data set, and what it is, it's basically the hello world of machine learning. It's commonly used as an example simply because of how easy it is to work with. And what this represents is, I believe, 70,000 images of numbers written by high schoolers. And so what we actually do here is we're going to take a look of how high schoolers have written these numbers, and we're actually going to take a look at some of the images here. And so this will take a while here, as it's kind of import. It's actually downloading the data set, and then what I do after is I call it the keys method. And what that basically does is it basically shows us what kind of keys we have. So like it'll tell us like our data, our labels, our tags, and so on and so forth. And so what I actually, and while that's downloading, I guess I'll explain what's going on here. So while that's downloading, I'm going to set X as the data frame or as the data frame, and then Y will be our target or I guess our label. And so I just made this comment here. So yeah, so basically each image is a 28 by 20, image. It's made by 20 by 20 pixels. And you have 70,000 of these. So that's quite a big data set, isn't it? And I guess that's sort of the motivator for using gradient descent here, because we're kind of working with this rather huge data set. And that looks like it ran. So now running this, what I've done is I've taken X, Y, I've taken the data and target, and I put them in their respective variables. And then what I actually do here is I make X a numpy array. And again, you need to have, so the issue with your dependent variable is you have to have that as a two-dimensional array. So once again, I'm kind of doing the same thing where I make it a two-dimensional array. But moving on to the more, I guess, main part of this is, so firstly, in MNIST, the first 60,000 images are trained data. So they're actually the data we already know what that is. We already, like it's basically just like what the model has already been given, right? And then the last 10,000 images are basically images we can use to test our model. We can use it to test what machine learning, our machine learning model. And so what I've actually done here is I've created two variables, train X, train Y, and they're taking basically the they're taking the first 60,000 and they're putting it into those variables. And so we're taking all the trained data and we're putting it into these variables. And then I kind of do the same thing here with test.x and test y. In fact, I should probably name this better just for clarity. And so I basically just take then the last 10,000 and put them here. And so let's say, for example, right, we want to see if any of our y's, or how many of our, if our y's can accurately predict what an 8 is, right? So what I'm going to do is I'm going to use something called test result 8, and I'm going to check if items in the list are equal to 8, right? So what this does is it creates a list of true and false values, and then you might have some true, some false, depending on whether or not they are considered an 8 by our 60,000, training images. And so right here, what we do is we first create these stochastic gradient descent classifier. And so we do that by calling this classifier here. And then this random state here just sets it to a random state. You don't need to worry too much about this for now. Just understand that this is just basically just initializing it. And much like what we did for our linear regression model, we're now fitting that data to our stochastic gradient. So we're actually using our training data X, and then we're actually comparing that to which ones are, 8 or not 8. And so what we do is we're basically fitting that into this. So we're predicting values, and so given a bunch of Booleans, given it if they are 8 or not, we're training that on our X, so we're testing it with our X, or yeah, I guess training, yeah. And so now what I do here is I pick a couple of, so I basically take any of the 10K images or 3 of the 10,000 test images. So this is what this random thing is just doing here. And then depending on that image, I basically change it to a 28 by 28 array. And that's actually how we, see these things. It's a better way to visualize it. And so then I basically just plot it using these several functions here. And so if I run this example here, I think, probably take a little time. Let's see here. I guess while this is loading, does anybody have any questions so far? That one was a load of words. All good so far? Okay. So wait, right here. So here's a couple of examples, right? So we've taken 3 images, right? And so now we're printing whether or not that is indeed an 8. So you can see that this one, it did correctly identify that that's 8. It did correctly predict that that is indeed an 8, right? and in this, it did correctly predict that that is not an 8, and that's not an 8. And you can kind of tell that this is really, really bare bones since we're only comparing 8s. We're not really, doing much beyond that. Like maybe, I don't know, we want to compare like train Y is also, like 9 or something, or it's also, 10 or no, just 9, sorry. Or maybe 7. Yeah, we'll just like maybe we want to compare if it's 7, 8, or 9, right? Oh, I keep forgetting syntax. Excuse me, guys. Well, regardless, I think we can probably just. I probably won't. I'll probably just see if I can do this, and if I can't, I'll just go on ahead and see what we can do. Or why don't we just change this to 7? See if we can do that. And maybe we're picking 3 random points. While that's loading, is it? I guess while that's loading, what I want to do is I finally want to show you an example. So our model can kind of predict, right? It kind of knows what 8 is based on all that data we've given it. And here's just an example of gradient descent. It basically just does a bunch of iterations. It goes over and over and over and tries to find the minimum cost. It tries to find, how do I get the minimum amount of inaccuracy? But this example here, I'm not sure if you can see that quite well. So I've ran this model, and you can tell that, and most of you here, and if not all, can tell that first one is an 8, right? But apparently our model can't. And if you notice, our model actually thinks that 8 is false, but it does correctly identify the second 8. So that's also part of the issue with just kind of doing this, kind of slapping it together, that we have problems where, although it should be an 8, we recognize it as an 8. Our class, our model doesn't actually think it's an 8. And so that's some of the issues we might run into doing something like this. And so I guess to actually solve this, you can use something called a confusion matrix. And it basically, categorizes, how different an 8 might look from another 8. So like you can kind of compare the 2 8s, and you'll see that one's a bit more clear than the other. But I guess for the sake of brevity, I won't talk much about the classification matrix or confusion matrix. I'll just briefly say that although this model does kind of work, right, this is kind of a pitfall of it, that, you might have 8s that are sloppily, well, I might be insulting here. I guess you might have 8s that, are quite different than other 8s, and it might, give you a false negative. And I guess let's check on our model again. So we just did a test on a 7, and these also all came out false, which again, that's good, I guess, but we're just comparing 7s. It's kind of bare bones, isn't it? But anyway, I guess that's just what I wanted to show as an example. And final words, where to go from here. So if you are looking for data, right, obviously my CSV file wasn't the greatest example. And if you really would prefer real life data, I would recommend some of these data sets. I can probably find direct links if anyone would like them later. And in fact, I'll also post slides too later if you guys would prefer that. But anyway, here's a couple of recommended data sets. And this will give you a good amount of data to work with. So, if you're interested in doing machine learning for other kinds of data or topics, feel free to take a look at those and you might get an idea. I guess the other question is what about computer vision, right? I know that's also, that's pretty common for machine learning. Yeah, sure, we mess with values, but, some of you might be more interested in computer vision, right? And how that actually works. So my suggestion is look at OpenCV, and also I kind of suggest here another library, TensorFlow. So I would look, but I would primarily look for computer vision anyway, into OpenCV. They have a lot of functions, and they kind of already have a lot of predefined things specifically for computer vision. So identifying shapes, objects, so on and so forth. And you can also use that in conjunction with TensorFlow. I'm not sure if you can with scikit-learn, but I'm sure there's a way. And finally, list of libraries. So although in this tutorial we use scikit-learn, there's TensorFlow, which is quite powerful. You can do stuff like deep learning, convolutional neural networks, and there's a lot you can do. But you can use TensorFlow, although it's mostly written in C or C++. You can definitely use it in Python. Python has an interface called Keras, and that's actually just the implementation of TensorFlow into Python. But anyway, these were my last words. And if you need to sign into today's meeting, please feel free to go ahead and do so. And with that, thank you. Any questions at all? No? Okay. Yes. Well, I think, so disclaimer here, I'm not an expert. But I think part of the problem with, so you're asking how you would implement a data set?
Yeah, like, I guess, like, after you mess around with you, and you want to, like, create your own data set to, I'm guessing, incorporate with it in a model, what's the best way to do that?
I guess, hey, Nico, is it still live? Okay. Yeah, just checking. So for those online viewers who didn't hear, he asked, how would you get data sets, or how would you make a data set?
Yeah.
So again, disclaimer, I'm not an expert, but I think the main issue with that is it's a lot of data collecting. So you can't just arbitrarily grab data. And that kind of goes back to our statistics talk earlier. The data is really, really important. You want to make sure that your model doesn't commit any of the sins I've talked about earlier, right? So, you don't underfit, you don't overfit, you want to have decent quality data. So I guess to answer your question, you could import stuff from another library or another database full of information. And although you could make your own, that would definitely take a lot of statistics. And if you want to go that path, by all means do so. Just know that it'll probably be difficult to make one from scratch, since there's a lot that goes into it. But again, disclaimer, I'm not an expert. No problem. Any other questions? We're all good?